Hi, I'm Max Corbell, and today I'm going to introduce a better way to develop hardware called ROHD, the Rapid Open Hardware Development Framework. ROHD is a new project aiming to revolutionize the hardware industry and replace SystemVerilog for both design and verification. ROHD is a publicly open source project on Intel's official GitHub account. ROHD is a generator framework. ROHD is capable of generating logically equivalent, structurally similar, human-readable SystemVerilog for hardware models. It also includes a fast event-based simulator with X and Z propagation, cosimulation with SystemVerilog simulators, and waveform dumping. You can develop using ROHD in a modern software development environment with modern IDEs like Visual Studio Code. Early measurements enable huge productivity gains, such as developing hardware on up to a 50 times faster schedule, writing the same functionality in 50 to 90% fewer lines of code, building your model over 150 times faster, and running your simulation over 8 times faster. Many people may be wondering why it's necessary to overhaul so much legacy, which has been effective for so long. First, SystemVerilog is just not good enough for our needs. It's too limited for hardware description. Today, many people use tools for hardware generation and connectivity due to SystemVerilog's limitations. It also has poor debug tooling. Most who have had significant interactions with SystemVerilog know how frustrating the cryptic error messages can be from vendor tools. But beyond that, there's very limited support for debuggers, profilers, breakpoints, IDEs, etc. SystemVerilog is also a poor language for test benches. Test benches are software, even if some don't think of it that way. Nobody writes any software in SystemVerilog unless they are a verification engineer because it's not a great option for software development. We just use it because it's convenient to interact with hardware and related tooling in the same language and tool stack. Test benches should be written in a modern, fully featured programming language. Also, test benches should run as software natively, rather than being passed into some separate black box tool to be executed, which reveals only limited information about the run. Integration and reuse are way too difficult. It's not unheard of for projects to take weeks to months to integrate a new version of the same IP, which is unacceptable. Hardware development suffers from very slow iteration time. By iteration, I mean the time from when code is changed to finding out if the change worked, which usually involves a build and simulation. Smaller IPs might need to wait only tens of minutes or hours per iteration, but large SoCs can take days to iterate. There are some other alternatives out there, such as Chisel and CocoaTB, for example, but none of the existing alternatives really address the entire set of problems. Some treat verification as second class, which is strange since we spend twice as much effort on verification as design. Some solutions are academic in nature, but not ready for production. We need an execution-ready solution right away. The open source hardware community is nearly non-existent. You may find some open source generators or cores, but they have varying quality. It's tough to find many open source verification components, and there aren't even any open source free tool stacks that can run UVM test benches. This means hardware engineers are often unfamiliar with open source development, which is a shame. The software industry figured out a long time ago that collaborating on open source projects, even with competitors, is a worthwhile investment. Hardware engineers spend too much time on the wrong work, struggling with bad tools and infrastructure. Teams should be focusing on their competitive advantages instead of bad tools. These problems are crucial to solve for productivity in the hardware industry. So let's get into how ROHD addresses the problems. ROHD is a framework written in a modern, general-purpose programming language called Dart. Dart is developed by Google. It's about 10 years old, but it started really gaining popularity in the past few years due to another Google-developed framework for cross-platform app development called Flutter. Dart has good asynchronous capabilities without requiring multi-threading, which makes it easy to model and interact with hardware. Dart is also fast, has a just-in-time compiler in a virtual machine, and supports ahead-of-time compile to native binaries on many platforms. Dart Dart also has a bunch of nice modern language features like type inference and null safety. Dart is easy to learn since it takes inspiration from other popular programming languages, and it has great documentation and tutorials. ROHD is not a new language. It's not an HDL nor a form of high-level synthesis. It's a generator framework. Rather than compiling from software into hardware, ROHD enables generation of hardware by instantiating and connecting objects with unrestricted software, including functions, classes, collections, recursion, and all your favorite design patterns. Unlike in SystemVerilog, where you need to consider whether certain language constructs are synthesizable, in ROHD, none of your code is synthesizable. Only the objects representing the hardware model are. That means you can use any software tricks to control your hardware generation from a full-purpose programming language. ROHD supports an extensible generation functionality, which maps each hardware object one-to-one with a generated output. The one-to-one generation means that generated SystemVerilog is structurally similar, human-readable, and maintains signal and port names. ROHD can also be used to generate other outputs, like related power information via UPF or other intermediate representations, like circuit. ROHD also includes a built-in, fast, event-based 4-value simulator. It includes a waveform dumper and supports cosimulation with SystemVerilog simulators through VPI. Synthesizable primitive or custom objects define both simulation functionality and conversion behavior. The simulator is responsible for initiating events at arbitrary timestamps, which propagate through the design. The synthesizers are responsible for parsing the model hierarchy and generating corresponding output code, such as equivalent SystemVerilog. IP integration is super simple with ROHD. Connecting two IPs with a common interface is a one-line affair. Integrating an IP is as simple as importing it. The diagram on the right shows how you can mix and match hardware and test bench components in both ROHD and SystemVerilog. The green boxes are ROHD, the purple boxes are SystemVerilog. You can have a ROHD design with some sub-IPs in SystemVerilog, co-simulate it all together with a ROHD test bench, convert the whole design to SystemVerilog, simulate it with some other test bench components in a larger IP, and pass the generated Verilog to downstream tools. There's a lot of combinations, making for an easy adoption path depending on your needs. Verification collateral is much easier to develop with ROHD. You can write your test benches in Dart using a UVM-like framework called ROHD-VF, which I'll cover in more depth in a future slide. Your test bench runs as native Dart code, meaning you can debug and profile it easily. And it executes in the same thread as your hardware generation and the simulator itself. ROHD includes convenient abstractions for automating your design, including pipelining, finite state machines, and more. ROHD supports abstraction via composition, which means that you can combine lower level abstractions to reach higher levels of abstraction. You can create complex abstract automation and generation without starting from the lowest RTL level code. However, you always have access all the way down to signals and gates, just like in SystemVerilog, so you don't have to give up any low-level control when you do want it. Dart includes an excellent package manager called pub. There's a public instance of it hosted at pub.dev, where ROHD itself is hosted. It is also possible to host your own instance for enterprise use cases with non-public dependencies. The pub package manager enables automatic dependency management and makes it easy to share code without friction, whether it's software, test bench components, hardware, automation, or anything else. With ROHD, you can leverage the fast and simple Dart build system. Forget your SystemVerilog woes with elaboration options, analysis options, defines, file lists, library ordering, etc. There's no need for any complex build systems. You don't need any proprietary EDA vendor tools with cryptic error messages. Just click run and your code will execute. You can develop all your code in a modern IDE with excellent language integration. On the right is a screenshot of Visual Studio Code, one of my favorite IDEs, but there are many to choose from. Dart has an excellent static analyzer that has great linting and integrates well with IDEs. The hints it provides help you learn the right way to do things as well. You can also use Dart debuggers, profilers, etc. to accelerate your development and debug. Let's quickly cover a little more detail about the implementation. All modules in ROHD are classes, which extend the module base class from the ROHD library. The hardware hierarchy is determined by connectivity between module inputs and outputs. There's no software reflection, and signal names are explicitly defined strings. This means that you can use any software mechanisms, design patterns, collections, etc. to generate the hardware, since the structure of your code has no impact on the hardware model. By default, modules functionally compose based on their connectivity. The functionality of a module is defined by the functionality of its submodules. However, you can also define custom behavior for a module by providing special instructions for how to generate an output and functionally simulate. All simulation occurs through arbitrary events, registered at arbitrary times. For example, you could tell the simulator to change the value of a signal at time 10, and then print a message to the screen at time 15. Logical simulation occurs by propagating signal changes through signals and modules, where each module is responsible for calculating its own simulation functionality. This example demonstrates some aspects of the power of ROHD, where writing equivalent design code in SystemVerilog can be challenging or impossible. The ROHD module, tree of two input modules, is a succinct representation of a logarithmic height tree of arbitrary two input, one output modules. The constructor for tree of two input modules accepts two arguments. Seek is a Dart list of arbitrary length of input elements. List is a Dart collection, and logic is a logical signal in ROHD. Op is a Dart function. In Dart, functions are first class and can be stored in variables. It expects a function which takes two logic inputs and provides one logic output. The module dynamically at runtime adds ports of appropriate input and output widths to match the count and width of the input elements from seek. The module recursively instantiates itself, but with different numbers of inputs each time. The base case is just a pass-through. Otherwise, we instantiate two instances of itself recursively, giving each of them one half of the input elements from seek. We give both instances the same operation to perform, and then inline get the outputs of those modules. We then perform the operation on the output of those two instances. We can instantiate an example of this module to find the largest input to the module. This code generates a list of 16 8-bit logic signals. The operation to be performed, op, is to create a mux, which returns A if A is greater than B, otherwise B. We can convert this module to equivalent SystemVerilog. ROHD knows that SystemVerilog can't produce a dynamic number of input ports, so it created multiple definitions with different numbers of input ports. They don't all fit on the page, but there is one with 16, this top one here has 8, then there was a 4 and a 2 input one, and then this bottom one has 1 input. Notice that the generated code matches exactly one-to-one with the modeled hardware. The pass-through maps exactly to the bottom one input version. The two instances of a submodule map inside the common case modules. And note the type is _1 inside the _2 version of the module. You can even see the arbitrary functionality inserted from the mux generated here. This is just a toy example, but it shows some of the powerful things you can do with ROHD. The ROHD Verification Framework, or ROHD VF, is a separate open source framework for developing scalable test benches in Dart with ROHD. You get access to the same ROHD simulator. Your test bench code is native Dart code, so you get all the great benefits of Dart and ROHD mentioned before, including fast and simple build, excellent static analysis and IDE integration, debugging, profiling, etc. You can build test benches that are structurally similar to VM test benches. So you get drivers, monitors, agents, sequences, etc. But you can skip all the macros and boilerplate. ROHD does not re-implement the full or exact UVM API. In general, ROHD is less opinionated and focuses more on the most valuable portions. ROHD takes full advantage of the native Dart language asynchronous support. This means that you can use futures, async await syntax, streams, and more. These are like more powerful modern alternatives to tasks, work joins, and analysis ports from SystemVerilog UVM. Importantly, the test bench does not convert to SystemVerilog UVM. This might seem like a limitation at first, but in fact, this is a great thing because it means you can write your test bench in Dart without thinking about how it might have to convert to a less powerful language like SystemVerilog UVM. You can write any software you want as part of your test bench in a fully featured modern programming language. ROHD is already being used for a variety of purposes, including microarchitectural modeling, test bench development, hardware design, and more. Multiple teams within Intel are using it today. And there are multiple users outside of Intel as well. Since it's an open source project, we can't know what everyone is doing with it outside of Intel. But we can see statistics on GitHub clones, stars, issues, and page visits, or when some of them reach out to tell us. Many of ROHD's benefits are qualitative and difficult to measure. For example, ROHD promises better debuggability, faster iteration time, and overall more enjoyable and productive development experience. However, there are some areas which can be quantitatively measured, even though they don't convey the full benefits that ROHD provides. These measurements are not exactly apples to apples comparisons, but it's as close as we could reasonably get. This table shows some metrics related to the re-implementation with ROHD of a relatively small, configurable, parameterized IP used in upcoming Intel Silicon products. From the same high-level architectural and interface specifications, what previously took about 1/4 to develop only took a couple of days with ROHD. The design had a dramatic reduction in the number of lines required, enabled by layering application-specific abstractions, only requiring about 30% as many lines of code as the original design. The build time for the re-implementation was over 180 times faster. And that includes the design, the test bench, and for ROHD, all of the SystemVerilog code generation as well. For simulation performance, one of the longest randomized stimulus tests was selected, which actually gives an advantage to the vendor simulator. Even with that advantage, the ROHD simulation was over 8 times faster on a laptop versus the vendor simulator on a server. This next table shows the differences in number of lines of code for real Intel designs in their original implementation compared to a re-implementation with ROHD. Two interfaces shown have dramatic line count reductions relative to their original TICL implementations. IPD is a highly parameterized and configurable IP, which historically has relied on defines, generate statements, and macros to achieve its configurability. Re-implementing a highly configurable IP with ROHD yields some of the best benefit. The same functionality was implemented in about 1/10 the number of lines. These line count reductions were not achieved by squishing down to get the smallest files possible. They are commented files, and the Dart auto formatter has been applied to keep the code consistently clean and readable. There are also configurable designs being developed which have large portions of the logic generated from machine-readable specifications. Huge improvements in iteration time and productivity are not easy to measure, but these example results can hopefully convey that there's some enormous upside to leveraging ROHD for hardware development. Both ROHD and ROHDVF are completely free, open source projects on Intel's official GitHub account for anyone to use inside or outside of Intel. They're also hosted on the public Dart package manager at pub.dev. ROHD is not yet another proprietary tool. ROHD is aiming to become a new industry standard. An additional key goal of ROHD is to encourage hardware engineers to engage more in open source. We can collaborate better across company and organizational boundaries and reduce the effort duplication while increasing the quality of our tools, so everyone can focus more on what matters. As hardware engineers, understanding software and open source also helps us understand our customers better. Today, ROHD is being shared internally and publicly, and we are growing a community around ROHD. Apart from direct usage of ROHD, people can contribute new packages, either open source or internal. These packages can be entire IPs, hardware components, automation, abstractions, verification collateral, or anything else. People can contribute to the ecosystem by filing issues, bugs, feature requests, pull requests, etc. for existing packages, or embark on new package development. Getting started with ROHD is easy. Everything is free and open source, full documentation is available, no licenses are required. The ROHD forum runs monthly as an hour-long meeting discussing ROHD development, and it's open to anyone to join. There's also a Discord server for ROHD open to anyone to talk about anything ROHD related. Links for both of these are available on the ROHD GitHub page. ROHD and the entire ecosystem are open for contributions from anyone interested. This is a great chance to do things the right way, starting from a clean slate. If you're an expert in an area, this is an opportunity to make some big innovations by being untethered from proprietary legacy tools. There are more big innovations in the pipeline from a variety of areas. The whole industry is up for disruption. ROHD can be used for small pieces of a design or test bench to start out. It doesn't have to be all or nothing. It's simple to mix and match ROHD and legacy code. There's a low cost to trying it out, and people who have used it so far have been thrilled with ROHD. I encourage you to try it out too. Please reach out if you want to discuss using or contributing to ROHD. There are also multiple ways to engage with the community listed on the ROHD repository. A solution like ROHD is necessary to keep us productive as hardware engineers. We can work together to make a better hardware development experience for all of us. Thank you.